Hello there. Today we're going to look at Promptbreeder, self-referential self-improvement via prompt evolution. This is a paper by Google DeepMind, which is the new conglomerate between Google Brain and DeepMind. So it should be fun. The basic idea behind this paper is that rather than writing your own prompts for large language models for them to do a particular task, you have a system that evolves prompts by itself. So you just kind of give it the description of a task and it comes up with its own prompts in order to have a large language model solve the task. Obviously, the coming up with its own prompts is also done by large language models and is done via an evolutionary algorithm. The evolutionary algorithm, if you know evolutionary algorithms, they rely on sort of mutation and fitness evaluation. And in this particular paper, even the mutation part is done by large language models. And so that's what makes it self-referential and self-improving, is that it improves its own method of generating improved prompts. We're going to look into this. It all gets a little bit complicated, not necessarily complex, but complicated in the sense of, what are you actually currently doing? Because every single thing is handled by a large language model. But we'll dive into it at the end of it. It's not that complicated. And while the results seem promising, if you dig a little bit into them, in my opinion, it's certainly not the end of the problem. Like, we haven't solved the problem at all. It just kind of pushes the problem into a different domain. And if you look at the actual results, I kind of have a hard time believing that, this here is the solution. There's something going on maybe, but they do see considerable improvements. So we have to give them that. So the authors here say that strategies like chain of thought prompting can dramatically improve the reasoning abilities of large language models. So rather than, let's say you have a family of tasks, like little math tasks, right? Peter ate 2 apples and Peter ate 3 apples. How many apples did Peter eat? You can just ask this to a language model and it'll tell you. Maybe it's even correct. But what people have noticed is that you can dramatically improve the final answer of a language model if you say something like, how about you think step by step? You tell that to the language model, and what you do is you kind of force it to break down the problem into small chunks and then perform these chunks individually and explicitly. And via various techniques of doing that, you can get a much better likelihood of the final answer being correct than simply asking your problem in the first place. So these various prompting techniques, chain of thought, tree of thought, step by step, and so on, all of this people have come up with. They had to sit down and think, and that's what they call here. These are handcrafted prompt strategies. And even though they work, they're often suboptimal. Promptbreeder, which is this paper, they call is a general purpose self-referential self-improvement mechanism that evolves and adapts prompts for a given domain, with the point being that this is no longer a manual process for us to sit down and think, okay, how am I going to write this? Please solve this math problem. Think step by step. Each line, write the formula, write the results on, and so none of this anymore. All of this coming up with the correct prompts is now being done via this mechanism here. The mechanism, as I said, is evolutionary algorithm to evolve task prompts. And the clue of this paper is the Promptbreeder is not just improving task prompts, but it is also improving the mutation prompts that improve these task prompts. So that's the self-referential part. They introduce again saying prompting is central. Prompting is central to the downstream performance of foundation models. Okay, so if you buy into this ridiculous term of foundation models, then in my opinion, this here is used slightly incorrectly, because prompting specifically refers to language models, and it actually doesn't refer to foundation models. So nothing there are models that I can prompt, which can be classified as foundation models, but also models that would certainly not be classified as foundation models even by the vague original terminology around that term. And there are foundation models that cannot be prompted, at least so far, according to the definition, the vague definition of the foundation model, I guess, marketing department. It's not really a research organization anymore. So yeah, that's just a pet peeve of mine. But fine, prompting is important. We get it. But prompt strategies are very manually engineered. So people have asked themselves, can this prompt engineering be automated? And there have already been papers into that direction. The automatic prompt engineer, or APE, I don't know how you want to call it, is an attempt into this direction. So they generate an initial distribution of prompts using another prompt that infers the problem from a number of input-output examples from the dataset. So you have input-output examples. You take a part of the dataset as a training set, let's say, and those are your demonstrations of how it's done correctly. And from that, you try to infer a prompt that would, I mean, it's sort of like it's like very classic machine learning. You take a set of examples of how it's correctly being done, and then you train something that would give you the correct prompt for that. So in that sense, the prompt here is like the weights of a regression in the classic sense, and the examples will be like the data. Yeah, it's a weird world, but that people have tackled automated prompt engineering like this. However, those things have given sort of these diminishing returns. So as they go on and on, trying to improve and improve and improve the prompt, at some point you sort of hit ceiling relatively quickly, and that's it. The authors here say, we propose a solution. Sorry about that. We propose a solution to the problem of diminishing returns via diversity maintaining evolutionary algorithm for self-referential self-improvement prompts of LLMs. So they say the reason why the previous automated prompt engineering efforts haven't worked out well is that they didn't maintain diversity as they improved their prompts. They just sort of improved, and then at some point with the initial boost to the prompt, if you go into that direction, there's kind of a limit. But maintaining diversity is a very well-known technique in a lot of these sort of exploratory black box optimizers, and that's what they do right here. If you want to know more or learn more about these things, there's a lot of work on open-ended learning and I guess goal-free learning and things like this. Works originally by Kenneth Stanley and people around him. I've made videos about this stuff before, and it's highly interesting. So there's a wealth of things to be explored in this direction. And this paper here goes a little bit into that, in that it says, hey, we want to maintain diversity of solutions, because what happens is when one gets into a point where you can't improve it any longer, you may be able to take some ideas or approaches from another place because you've maintained that diversity, port that over or combine two solutions, and therefore improve even more, rather than getting stuck in some I forget how it's called, like a street where you can't move on. I don't know the English word right now, blacking out. So the results are the first thing they show right here. You can see that in various data sets there, which is PB here, in zero-shot and in few-shot learning, or in few-shot inference, they trump the other methods, or largely surpass the other methods. Yeah, now to be said, in some of these things, for example, the star here, it's not the original number if you want to compare that to other papers, but they have sort of subdivided it into training and test samples. Yes, we we are back in the world of training set and test set. LLMs, if you just use them in zero-shot fashion, they can actually solve tasks sometimes. That's what the original paper, large language models are strong multitask, zero-shot, something like this, learners was. GPT-2 paper maybe? Or GPT-3? I don't know. But we're back in the world of actually using training data. So the way that these prompt improvement systems work is by consuming training data. Training data of successful executions of the task. So how does Promptbreeder work? This is the overview that they give right here. It all starts with a initial set, initial population, that's up here. So initialization of the population of task prompts and mutation prompts. So they have two kinds of prompts. Actually, I have three kinds of prompts. Actually, they have three kinds of prompts and then some constant prompts. There are these thinking styles right here. It's a bit weird to me why they're here. Like in principle, I can totally see that at some point this just probably didn't work as well as it should, and then they just introduced, said, how about we just kind of introduce different thinking styles to even up the diversity even more. But the thinking styles, that's just a list of like thinking styles. One is like, let's think step by step. Another one is they have a list down. They have the list down. These are fixed. They're just a list of different thought heuristics, not specific to any problem whatsoever. Just like, try to think outside of the box or something like this. Try to reformulate, or try to break the problem down into different sub pieces or so. Thinking styles. Yeah, completely irrelevant to here, except introduced probably to make it work better. The problem description is very specific to the task you want to solve. For example, solve this math problem, give the answer as a number or something like this. This is a problem description. And then obviously the so-called mutation prompts. The mutation prompts are, can I take one prompt? Sorry, that's an R. I wanted to make a P. Can I take a prompt? Can I make it into another prompt via a mutation prompt? So the way that works is you take a large language model and you feed in the mutation prompt plus the prompt, and the output is going to be the next prompt. So the mutation prompt is going to be something like this. Change this instruction to make it more fun. That's a mutation prompt, because you can concatenate it with a prompt, and they have this structure right here. So they put the word instruction here, and then the problem description, and then instruction mutant, right? So you kind of coax the language model into giving you a variant of this prompt right here. Now, at the very beginning, they just mutate the original description of the task, like solve this math word problem. But as the algorithm goes on, this thing right here, this original task description, has also changed. So these things here are P, the prompts, and then these things here, these are M, the mutation prompts. Both things are going to change. So the prompts are going to improve, and the mutation prompts are also going to improve over time. At least that's the idea. So those are the sets of things that take part. There are prompts, there are mutation prompts, there is the original problem description, there's a list of thinking styles, there is a little bit of structure into, for example, here, instruction mutant, like the meta prompting, so to say. And that's it, except for the mutation operators down here, but we'll get to that in a bit. So the initial population we just generate like this. We take the original problem description and we use a initial set of mutation prompts, and we just generate a bunch of variants, right? Now, one thing that wasn't very clear to me when I read the paper initially was the following. they have what they call units of mutation. And a unit of or a unit of evolution. A unit of evolution is a mutation prompt, and as far as I understand, and two, P1, P2. Two prompts. So the mutation prompt could be something like we just saw, like reformulate this instruction to make it, I don't know, better, to make it more fun, to make it more concise, something like this. Then P1 and P2 are actual prompts, like solve this math problem. And however, those two are used in the following, at least for most tasks. That's how I figure. It's not super duper clear, but when you actually get the task, like at evaluation time, what you do is you write P1, then you write the problem, like the actual, here is the math question. Then you let the LLM produce something. So you let it produce something here. So this could already be the solution, but then you put prompt 2, and then you let it produce something else. And this down here is what you check for correctness. So you have, for example, the chance of instructing to solve the problem, and then this here, bring it into the correct format. Like that's a very common approach. So first, you just instruct it in some way to solve the problem, and usually these LLM, they'll put out something like, here is the solution, and then they give you the solution, and what you wanted was just the solution. So people have started to put into the initial prompt like, only provide the solution, blah, blah, blah. But it works also equally well if this really just focuses on solving the problem, and then this focuses on getting into the correct format of the solution. But there are other things thinkable. But essentially, these two prompts together, you can think of sort of like the prompt, except that you structure it in this way, that you first put the first prompt with the problem, you let the model produce something, then you put the second prompt, you let it produce something again, and that's what you check for the answer. Another thing, apparently the APE paper introduced this format. Another thing that makes it even harder to compare to just like zero-shot prompting, where you just say, please solve this problem, right? The chance that you have two prompts here and you kind of interleave them. In any case, that's how they do it. Now, why do they call this thing here a unit of evolution? They always evolve these together. So one mutation prompt goes with one actual task prompt together. And that's not really necessary. You could just maintain a population of mutation prompts and a population of task prompts, kind of. But they do it because they always need to evaluate fitness of these things. If you know about evolutionary algorithm, you maintain a population of these, and you want to know what's the fitness of these. Like, how good are they? How good are these prompts here, and how good is this mutation prompt? Now, the prompts you can easily evaluate. You just take a bunch of data points, right? A bunch of questions from your training data set, as we said, and you evaluate it. And you check whether they get the correct answer. If they get the correct answer often for a lot of these data points, they're good prompts. The mutation prompt, however, is a bit more tricky. So the way you evaluate that is, because you have these things together, you save them in a way that I believe you always save the mutation prompt together with the prompts that it produced. The way you, and then it's really easy to say, well, if the prompts are good, that means at least in part the mutation prompt was good because it produced these prompts, and therefore it probably didn't do something stupid, right? You could also look if the new prompts that it mutated are better than the old prompts that it got as an input. But in essence, you keep those together because you need to evaluate the mutation prompts, and you evaluate the mutation prompts by proxy, essentially, by evaluating the prompts they produce. So You always keep them together, which is not necessary engineering-wise, but that's what they do. That's why you see down here, if you look at these things, this is your population right here, and this is an individual in the population, and you can see it's made up of a prompt and a mutation prompt, or alternatively, two prompts and a mutation prompt. And they have a fitness over here. So what do we do now? As the algorithm progresses, we're building up this population, as we said, and we have fitnesses. And usually what you do is you order these things by fitness, and then you just drop away the ones that have a very low fitness. So that thing right here, you know, out you go, and is replaced by another individual. The other individuals you get by taking the good ones in your population and mutating them. So you want to take the good ones, mutate them, and put them back, and then order all by fitness, evaluate everything, and then cull away the ones that have a very low fitness. That's how evolution-based, population-based algorithms work. How do they mutate these things? And that's where these mutation operators come in. So they have various ways of mutating the prompts themselves, and that sometimes makes use of that mutation prompt, right? Or evolving the mutation prompt as such. So this is where it gets a bit complex. These mutation operators, either they take a prompt and they make a new prompt, right? So then if you think of what happens to the unit of evolution, this unit of evolution is going to be MP. Let's just focus on a single prompt right now, not two prompts. MP, that's going to be MP prime, as far as I understand, right? It's also possible for them to take absolutely nothing and make up a new prompt, or just the initial task description. So in that case, also, you just replace one of the prompts with the new prompt with the same mutation prompt. Then it's also possible to take a prompt and a mutation prompt and produce a new prompt, right? That's why we have the mutation prompts in the first place. So in that case, again, the mutation prompt pair would be transferred into the same mutation P prime pair. So, and then it's also possible to take a mutation prompt and make a new mutation prompt. And then that you can use to process the prompt into a new prompt. So they have all these different things that they do to this population in order to change the population around. And they list them down here. So, okay, yada, yada, yada. And then, yeah. So they have 9 operators for mutation. The rationale for using this diverse set of operators is to enable the LLM to explore a large space of cognitive methods of linguistic self-questioning by repeatedly changing the framing of the problem, as well as retrieving mental models expressed in natural language that can help tackle a given reasoning challenge. So we'll go through the mutation operators, and yeah, keep in mind, these are things that they do to change the population around in between these rounds. So every round, they want to change the population, they want to mutate a bunch of the ones they have, add them back into the population, then order them all by fitness, cull away the bottom ones, and repeat again. And while doing that, so the mutation always concerns the prompts, but also the mutation prompts that are used sometimes to mutate the prompts. So, direct mutation concerns with just directly generating a new prompt, like a new P prompt, a new task prompt. That's what they call zeroth order generation. We generate a new task by concatenating the problem description with the prompt, a list of 100 hints. So this is like the very start when we just generated our initial list of prompts. We just do that again. So in that sense, we always have like a thing that generates prompts from the very starting problem description. So we don't kind of evolve into a place where we get lost and we have nothing to do anymore with the original problem, which could be a degenerate state. So they say it's regenerated from the problem description each time. This does not use any existing prompt. This does not use a mutation prompt or anything like this. This just generates new prompts and adds them to the population. Then we have first order prompt generation. Here is what they say: we concatenate the mutation prompt to the parent task prompt and pass it to the LLM to produce the mutated task prompt. For example, say that instruction again in another way. Don't use any of the words in the original instruction. There's a good chap. And the instruction is solve the math word problem, giving your answer as an Arabic numeral. So this is probably what you imagine when I tell you there are mutation prompts and there are prompts. And we use the mutation prompts in order to mutate the prompts. This is exactly it. So we give the mutation prompt, we give the prompt, and mutation prompt says something like change this prompt to be better, and out comes a new prompt. The procedure, they say, is identical to the initialization method, except that a randomly sampled thinking style string is not used. So in the initialization, you use like the thinking style, and here you don't. Now, so the whole point of this paper is kind of, can we do something hands-off that is not hand-engineered, so we don't have to think about this, this prompting thing, and it really depends on how you do it, so we'd rather not do that ourselves. Yet so many things in this paper are clearly done out of fiddling around because someone discovered, ooh, if I do it like this, it works better. Like, ooh, if I add the thinking styles at the beginning, then it works a lot better. So that's a bit my problem. I'd rather have had a paper that doesn't do a lot of the things that they do in this paper to make it better, but instead have sort of a more solid work of research, like a work of research that actually focuses on what if we just hands off do the most general, straightforward thing and see how far that gets. That would have been so much more valuable than, let's add in thinking styles, and let's add in this. And the fact that they have these 9 random mutation operators that they have like here, and the exact way they construct them is also pretty sure a result of kind of tinkering around and figuring around. So in my estimation, it just delays the problem to a different domain, namely to the domain sort of meta prompting and so on. And yes, probably it's like teaching a person how to fish instead of giving them a fish, right? But to me, it's a little bit too much focused on teaching a person how to fish that exact one fish in that exact one pond with the exact one fishing line I give them, and if they do it in exactly my way, and also I'm going to kill the fish first and kind of put it there so they can just grab it. Yeah. Plus the fact that obviously all of this uses training data, which is sort of against the sense of working with LLMs. But never mind. So then they have, they say, look, we can not just condition on 0 or 1 parent, but we can condition on a set of parents. So we provide a filtered and numbered list of the current population of task prompts to the LLM and ask it to continue this list with new task prompts. So they're just going to go through all their units of, mutation. Let's maybe back to the graphic. They're going to go through all of these right here. They're always going to grab just the prompts out of each, order by their fitness. So they have an ordered list by their fitness and provide that. And then they say, we could just let the thing continue that list, right? But they filter it, so they don't want things that are too similar. So if they're too similar, cosine similarities, they throw them away. So this is kind of a diverse list, encouraging diversity. And no, sorry, my bad. This particular mutation operator does not provide an ordered list, but just an unordered list that is focused on diversity by filtering out very similar things. This next one here provides an ordered list of the same thing. So this is a variant of the above, in which task prompts are listed in fitness order. So they say preliminary experiments showed that the LLM is more likely to generate entries that are similar to the elements appearing later in the list. They say we ordered the task prompts in the population by ascending order of fitness. So the most fit things are at the end, if I understand that correctly, where the LLM is more likely to generate entries that are similar to the end of the list. So the highest fitness are at the end of the list, and then they tell the LLM that this is a list of responses in descending order of fitness. Okay, so so they lie to they lie to the language model. They say they order it in ascending order of fitness, so that the last one, which they know the LLM focuses by default on, is the best one. But then they say, no, it's actually the other way around. So in the prompt, they say this is a descending order of fitness. And they even clarify it. They say this, that index is the best response. It resembles that more than it does that other one. So they really hard try to convince the language model that it's the other way around. Why? They say this is because otherwise it is too biased towards producing a new entry that is too similar to the final entry. The contradiction between the ascending ordering and the statement that it is a descending ordering appears to improve the diversity of sampling. Really, like, this to me here is the most staggering example of, I have nothing against this. I'm all for, weird tricks that, the initial ones were like the Unreal Engine tricks for the diffusion models. I'm all for that, but not in a paper whose explicit reason for existing is saying, well, these other things, they just do handcrafted random things that they just find to work, and that's not a state of being. That we should solve that problem. So here is like an automated system, hands off, so you don't have to handcraft weird things anymore that just kind of you see working. Yeah, not in a paper like this. I get it. It improves the score, but it, in my opinion, diminishes the value of this particular paper. The finding here, to me, is great and could be its own other paper of just saying, I found this weird trick, and that's very cool. In any case, as we go on here, if you see it in this slide, you'll see a lot of the same things. So here, they say, lineage-based mutation. We provide a history of the individuals in its lineage of a mutation, of a unit of evolution, sort of like, okay, here is how this particular unit evolved over time, the ancestors of it, like it was mutated and mutated and mutated and always remained in the population, which means its fitness probably increased over time. So they ask, well, could we just coax the language model into continuing that list and therefore make it even better? So they say, look, this is a genotypes found in ascending order of quality. And you may notice, now they don't lie. Now they don't lie to the language model. They just say this is ascending order of quality, and they actually provide it in a chronological order, which we know, given the evolutionary algorithm, is probably an ascending order of quality because the lineage always survived in the past. And why would you do the trick here and not the same trick here? Probably because they found in the first case it actually improves things on their particular problem with their particular method, and in the second case it probably didn't improve things on their particular thing with their particular method of doing it. Yeah, again, same thing. And then there's hypermutation. So that's how do we mutate the mutation prompts. There is 0th order, like 0th order prompt mutation is just we concatenate the original problem description with to a randomly sampled thinking style and feed it to the LLM to generate a new mutation prompt. So just using the thinking styles as sort of meta mutation prompts generate a mutation prompt. Again, why the thinking styles enter here, who knows? It just worked better, right? Which thinking styles are in the list? Just a bunch. First order hypermutation, we concatenate the hypermutation prompt. Please summarize and improve the following instruction to a mutation prompt so that the LLM generates a new mutation prompt. Again, this thing right here, I know it's quite generic, but it is a handcrafted prompt. And then you have Lamarckian evolution, where you put a bunch of examples of how it worked out previously and try to get the prompt out of this, and you have prompt crossover and context shuffling and so on. Techniques that are used in evolutionary algorithms in general. So their results are okay. They're better than the other automated prompt generation methods, and they're also better than, for example, hand design prompts. So they say this in this classification problem, this hate speech classification problem, Promptbreeder was able to involve a prompt strategy consisting of 2 sequentially applied relatively long prompts that scored 89%, an improvement over the hand design prompt, determine whether text contains hate speech, which scores only 80%. Okay. If I show you, I'm going to show you these prompts, but just look at what it says. This is the hand design prompt, is determine whether a text contains hate speech, right? I don't know how much time went into this, but it sort of can't be more than 30 seconds. And I already get 80%. Zero shot. I have never looked at any training data. I could come up with this right now, right? I already get 80%. In order to get to 89%, this entire apparatus is being used, including training data, right? Including actually taking data from the dataset and using it as training data, which is very expensive to collect often. Plus, we now don't have one prompt, we have 2 sequentially applied, relatively long prompts that were evolved via an evolutionary algorithm that uses LLMs on top of LLMs to evolve. And you get 9 percentage points out of it. Now, granted, that's like 50% less mistakes if you think of it like this, but still, we can actually go look at this stuff. So there's only the appendix remaining, where I want to show you a bunch of things. So here are curves. These are very typical of evolutionary algorithm. You start with generation 0, you evolve over time, and you see sort of the Pareto frontier improving and the average fitness improving, which is pretty cool. The mutation prompts, here's a list of mutator prompts that are, I'm going to guess, the initial ones, or the evolved ones. This should be described. It should be described somewhere. I'm not sure. I just found this one funny. Break free from conventional constraints that takes the prompt to uncharted territories. It's what is the world come to? Thinking styles. Here's a list of thinking styles. So something like, are there any stakeholders or individuals who are directly affected by the problem? What are their perspectives and needs? I mean, sure, but also this is completely engineered. But it is more general than I totally believe that I can throw this thing at various different problems and it will kind of do a good job at them, as long as they're sort of in the same meta domain as the problems that we see here in this paper. So take my criticism with a grain of salt. It is a cool work and is definitely a cool attempt. I don't want to denigrate the paper as such. And now, yeah, Look at some of these results. And that's gonna be my last quiz. Oh, here is the evolve prompt for this hate speech detection. Look at that. Look at that. You think like, okay, yes, that's probably going to be better than just saying, does the text contain hate speech? But if you read it, it's like, I wonder what a human could do by just spending 15 minutes, right? Yeah. Evolve mutation prompts. The top one is, please summarize and improve the following instruction. This is the most successful mutation prompts evolved in a self-referential way. You can see that the top scoring mutation prompt is essentially what you would come up initially. I mean, it's cool, but does it really necessitate this entire machinery? Also here, the mutation operators that are the most effective are 0th order hypermutation. So where you just kind of come up with a new mutation prompt. Lineage-based mutation is interesting that it's so high. And first order hypermutation also shows that, okay, reformulating the prompt in some way is important. What's also important is that there is no super duper dominant mutation operator here. That means all the mutation operators kind of contribute. That's a positive result, I would guess, for this paper. Even though the sort of 0th order things being at the top is probably it's probably more than was, or different than was hoped for, because what you hope for is sort of that the most intricate ones go to the top, and that those are the really important ones where you take a mutation prompt that was evolved already and evolve it more, and then use that to change a regular prompt, and that mutation is really, but I guess that's kind of this, if you think about it. Except that you don't, I guess this one here would be, yeah, that one here would sort of be the core of the paper. The first order hypermutation, where you mutate a mutation prompt, you use that to mutate a task prompt, and then that is really important. So I guess it's a good result. That's in third place. So here are some examples. After 1,600 mutations, and this is a 2-prompt thing, okay? That's what's evolved. Prompt 0 is the mutant, and prompt 1 is mutant. That's it. So the tasks are like, the tasks are, I don't even know what the tasks are, add sub, but it's like a bit of math problems. They say themselves, we find that in the few-shot evolution case, the contexts dominate and often the task prompts drift into nonsense. They're less critically determining of fitness than the evolved context. Oh, the evolved context, I didn't touch on this, but they also essentially evolve which few-shot examples get into the context, and determining those well, I guess, can make a difference. Of that being said, every time they use training data, they completely use in-domain training data, like the same distribution as the test data. Yeah, there are more. So there is math problems. Solve the math word problem, giving your answer as an Arabic numeral. Have you solved a problem like this before? Like, this is interesting. It's interesting that this is what works well, but also I have my doubts that is really the best prompt. It's sort of a self-assessment thing, but if you look through these examples, you could definitely, so these are also math problems. I would solve the math word problem without using a calculator, giving my answer as an Arabic numeral. Okay, that's a fine prompt, I guess. But then the next prompt is 1, 2, 3, 4. Yeah. And here, you just shout. You just shout at the language model and you hope that improves it. Okay, here is where I actually believe that this is a good prompt. Just shout and that's it. Here the first prompt is just kind of a date range. And this has nothing to do with dates. These are also math problems, as you can see right here. So doubt. Press X to doubt. Like, it's definitely cool work, but if you look at the actual results, it's sometimes questionable whether it really does something sensible, right? Or whether the results we see, like the good numbers, are more like there's something else that contributes to them that's just kind of the nature of these problems, or some kind of circumvention of this, and whether this is really the method that evolves these stellar prompts, especially as they could generalize to other things and do more stuff, and we could extend this method. I remain doubtful. Nevertheless, it is an actual cool work, and I'm very happy that people are researching into this, and I'm very excited where it goes from here, don't get me wrong. So thank you a lot to people from Google DeepMind for researching this, and I hope we can continue, and I hope the next steps in this are better and better and better. And at some point, we won't have to write prompts or meta prompts or hyper prompts or anything anymore like this. Excellent. Thanks for listening. Bye-bye.